All right. Hide floating meeting control. All right. Welcome, team. Welcome to another Data 100 lecture. Let's go ahead and get started. So today we have our second pandas lecture. As we talked about our plan for this 3-lecture sequence of pandas, today we're going to get a little bit deeper into different functionalities in pandas. In the previous lecture, we talked about different data structures. We kind of saw tools that are available to you in pandas, data structure series, data frame, and also index object. Today, we're going to do a little bit more digging into data frame specifically, and then we're going to see how we can do extraction a little bit more, because we went over extraction using iloc quickly at the end of previous lecture. So we're going to go and review that one more time. We're going to spend some time on conditional selection. So we'll see how we can do conditional filtering on data frames, and then how we can do that more efficiently with different compound logical expressions. We're going to get actually a little bit deeper and actually do things. So we're going to spend time on modifying columns. We're going to create columns. We're going to remove columns, and then we'll be able to apply some functions to gain some insights from different columns and different features that do exist on our data frame. And then quickly, we're going to see aggregation of data, or applying different aggregation functions on data frames, which is kind of the main topic that we'll touch on again in the next lecture, in the Pandas 3 lecture. So let's dive into things by talking about loc, iloc, and this context-dependent selection operator to see how we can filter our data frame or series for that purpose in order to extract a piece of rows and a piece of columns. We also want you to know that all of these functionalities that we're telling you, you won't appreciate the usefulness of them until a little bit later, especially when we're talking about exploratory data analysis and also a little bit more about them in the modeling part. So bear with us, just learn all of these mechanics that you need, and then you'll appreciate them more towards kind of week 3 of data 100. So this is the structure that we've seen for selecting or filtering or selecting a number of rows and a number of columns. We said that with a data frame, we have column labels, and then we also have row labels. All of these bold values that are at the top of the columns, and also in the first kind of column in the rows. All of those are called labels or indices for the column and for the rows. We can do selection based on the labels using the loc operator. So this is where using .loc, we pass 2 operands to .loc, and then we will be able to specify with the first operand what are the rows that we want to extract. With the second operand, we'll say what are the columns that we want to extract. In order to pass the labels for the rows and the columns that we want to extract, there are 3 different ways that we can pass those values. We talked about passing a list, so a list of labels for the rows and for the columns. We talked about the slice. Remember that there was a specific kind of anomaly in the Python contract, that here with the slice, we're saying that the syntax is inclusive of the right-hand side. So if you want to get, for example, rows from integer, from the label, for example, 0 all the way to 3, know that this is inclusive of the tree. So you can say 0:3 instead of saying 0:4, and then assume that 4 is not inclusive. In this case, with the label-based extraction using loc, it is inclusive of the right-hand side, which you have to remember that the specific is special case. Or a single value. We can always pass a single value and then extract 1 row or 1 column. And then we talked about the data structure for extracting 1 column, which is always a series for extracting 1 row. Depending on how many columns you're extracting, you might get a sub-data frame or a data frame object, or you might get a single value. Again, at the end of the lecture, I talked about another way of extraction. I said that sometimes we don't want to do extraction based on labels, based on those index values, but we want to do extraction based on the integer position. So iloc, I stands for integer-based extraction, so you can remember it with that. The mechanics is exactly the same. We can pass a list, we can pass a slice, or we can pass a single value, and then we'll be able to extract the data set that we, or the sub part of a data frame that we want. So it's still working with the elections data frame that we had from before. The elections data frame is the elections kind of data set from historical US elections, the candidates who ran, the year that they ran for presidency, the popular vote percentage that they got, and the result, whether they won or lost that election. So this is the data frame. If I go ahead and do integer-based selection or extraction using a list, I'll just pass two lists of integer positions. Notice here that I have one list here for the list of integer positions for rows. Rows always comes first, and then one list for the columns. So what you're seeing in this case is like all of the values in those lists are integer values, again, because it's the integer-based extraction. What you're seeing for the columns is that for the columns, I'm extracting the first column, second column, and third column. They're at integer position 0, 1, 2, and that's why I'm extracting column with label year, with the label candidate, and with the label party. So that's how integer positions do correspond with the sequence of columns that we have and with the sequence of rows we got. For the rows, notice that I'm saying that integer position 1, 2, 3, and it looks like that the label is also the same. Label is 1, 2, 3, as opposed to like what you're seeing for the columns, that the labels do differ with the integer position. This is mainly because we just assign labels automatically, and with automatic assigning of labels or index for the rows, automatically we'll start with assigning the first row label as 0, and then the second row label as 1, and so on and so forth. So integer position in this case is exactly the same as the label, but note that this is not always the case. We could go back and re-index this data frame and have different kinds of indexing. It's starting from 1 or having different categorical or like different string values for those labels. So it's not always the same. So this is the way that iloc is going to take two list operands in order to do extraction. We can also have a slice. So with this slice, mechanics is the same. We just pass this slice a range, starting from some integer position all the way to another integer position. And note here that this is exclusive of the right-hand side, which is the normal Python syntax. So in this example, instead of me providing the list 0, 1, 2 for the columns, here I'm providing a range or a slice. And this slice says 0 all the way to 3 and not inclusive of the 3, and then I'll be able to extract exactly the same thing. So notice that the row integer positions are at position 1, 2, 3, and the column integer positions are 0, 1, 2, and not inclusive of 3. So we get only 3 columns as a result. Okay. So what we also learned last time was that with the, again, normal Python syntax, if we don't provide the starting point of the range or a slice, it will start from the beginning. If we don't provide the right-hand side of the range, it will go all the way to the end of possible values that we have. If we don't provide any of them, it will extract everything that we have in the rows or in the columns, depending on what it is that we're extracting. What are we extracting here? So I'm using iloc. The first operand says colon, which means everything, all of the rows. And then the second operand says column at integer position 0 all the way to 3 and not inclusive of the 3, which means that I'm going to get a sub data frame with only the first 3 columns in this example. Okay. What we also learned is that the third way of doing extraction is using single value. So I can provide a single value or a single integer position for the row or for the column, and then be able to get a single row or a single column. If I get a single row, the data type of the output is going to be a data frame. If I get a single column, here I'm providing the integer position 1. This means that get the second column for me, right? And the return type is going to be the return type of a single column, which is what? What is the type of a single column? A series. So remember that data frame was the collection of different series objects. So in this case, when we're extracting one exact column, it is going to be returned as the object it is. So the object that it is under the hood is going to be a series object. So that's why you're seeing this series object. Obviously, this is a filtered version of that series object because we also filtered for the rows. So we're only getting row integer position 1, 2, 3, for that specific column, but the data type is going to be series. One way to tell apart whether the result is series or a data frame is the way that they're being printed. This is the way that the series is being printed versus if you print a data frame, it has the proper labeling of rows and columns, and you will be able to see this table-like structure versus with a series, what you're seeing is the index. You're seeing the values. It will tell you what that column label is and what is the object types of the objects that are stored or the values that are stored in that series object. Obviously, I can go ahead and provide a single value for the row and for the column that isolates my vision into only one cell or one row for one attribute. And then the return type is going to be whatever the type of that underlying data point is. In this case, it's going to be an object or a string that we're seeing at integer position 0, the first row, and for the first column or the second column because it's at integer position 1, and then it's the name of a candidate, Andrew Jackson, that we're getting as a result. Okay. So moving on, talking about why we are learning loc versus iloc. I briefly mentioned this. Loc is label-based extraction. iloc is integer-based extraction. Most of the time, you will use loc for two main reasons. First of all, a lot of time we might want to shuffle the data. We might want to like restructure the data that we have. And we don't want our code to be dependent on positionality of the rows and the columns. And because of that, what we're doing is we're using labels so that even if we move columns and we move rows, labels do not change. And then we can still use the same code as is. This is one main reason. The other reason that we might want to use it is for readability. So imagine that if I want to get, for example, a number of columns, and I give you a code that says that I'm extracting columns, candidate, year, and result, and then you'll be able to read it. You'll be able to see what features I'm using for modeling versus the case that I just say that, oh, go ahead and get the columns at integer position 1014. So someone who is reading the code is going to have a hard time figuring out, oh, what was the original data structure? How does it change? How does the data frame change along the way to be able to make sense of what the shape of the data frame or what is the data frame exactly that, and then what does it mean for us to extract row, the column 0, 1, and 4. So this is also another reason. iloc, on the other hand, can be useful in the cases that position has a meaning for us. So take into account an example that I have a sorted, for example, a data frame. Say, for example, it's the example that we have here is movie earnings or something like that, that you're sorting different values, right? And then the order has a meaning. So for example, if you're sorting in ascending order, the values will increase. So the maximum earning is going to be at the end, and the minimum value is going to be in the beginning. And then if you're interested in median, the median is at integer position in the middle of the data frame. So instead of writing a separate function to do that for you, you can just directly say iloc, give me the row 0, give me the last row, or give me the middle row of this data frame, and then you'll be able to get min, max, or median. So this is going to be helpful in those specific cases. So while it was all making sense, there is another shorter, more handy version of doing extraction, which we are referring to that as context-dependent extraction. You'll use it more frequently than you think, but as you can see with the name, it's context-dependent extraction. What it does is it is a kind of a combination of loc and iloc in a sense that it only takes one argument, and depending on the type of the argument, it will decide whether it is extracting rows and the argument that is passed is integer values, or if it's extracting columns and the argument that is passed that it has received is column labels or not. So having said that, it can take, again, only one argument. And then what happens is that if a slice is passed to this context-dependent extraction operator, it's going to assume that you passed row numbers. So if you, for example, have a slice and your slice is not a slice over integer values, or the integer values are not within the range of the row numbers that you have, you're going to get an error. So in this case, passing a slice, it will assume that they're row numbers, so we'll go ahead and extract row numbers, and then it will give you all of the columns. So notice that there's only one argument that this takes. This means that it will either do filtering on the rows or will do filtering on the columns, not both of them at the same time. If you want to do both filtering on the rows and columns, this is not the operator that you want, and you'll have to go with iloc and iloc. So passing a slice, row integers, we're going to filter for rows. We're going to get those rows with those specific row integers, and then all of the columns are going to be passed. If we get a list or we get a single value, it will assume that the value that you passed in that single value or in that list are all labels for the columns. So if the values that you're passing in a list or that single value is not a column label, you're going to get key error saying that there is no column with this specific label that you told me. Okay, that's how it's going to compile and under the hood execute all of these instructions that we're getting. It'll take time for you to remember all of these and then use them. We imagine that you might use iloc and iloc more frequently because they make more sense. And then as you're working through your code and you're writing more code, then it will be faster for you to just directly select rows, select columns, and then you will use context-dependent extraction in those cases. So let's see how that works in an example. So say I'm passing a slice. Obviously, a slice is a slice of integers. And what are those integers? Those are integer positions for the rows. So I'm saying that starting from 3 all the way to 7, and then not inclusive of 7, right? Because that's the default how a slice is going to be executed with the iloc operation, because this is an integer position. So you see, row at integer position 3, 4, 5, 6 is returned, and all of the columns are being returned in this case. Now moving on to a list. So I'm passing a list. Notice that this is a list. I'm passing labels for the columns. I have to pass labels for the columns. If I pass something else that is not a label for a column, say I pass a value of 0, I'll get a key error. So you have to make sure that the columns do exist. And this is kind of an easy way for you to debug your code if you're getting an error in your homework 2A or also in the next homework that we'll release on Friday. So we're selecting columns. So all of the rows are going to be returned. So again, this is only one dimension filtering that I want you to think about. What are the columns that are being returned? Year, candidate, and result. So all of the rows are there from row 0 all the way to 181. And then only these columns are in the output. If a single value is passed, that single value has to be a column label. And in this case, I'm saying that this is a single value candidate. Let's go ahead and get that single column, which we know is a series object. That's why the output type is a series. Okay, so in this case, I'm getting the series corresponding to candidate. All of those rows are being returned because I cannot do any kind of filtering in addition to this on the rows. Okay, so now is your time. Take some time to think about this example. This is a data frame. You can see how the data frame is created. It's kind of a tricky example. The name of the data frame is weird. It has 2 columns, 1 column with the integer label 1, 1 column with the string label 1, right? And then we also put different values in those columns. So for example, the first column with the integer label 1 has the values top dog and bottom dog, and then the other one has top cat and bottom cat. There is a series of 3 questions that we have, and starting with tell us what is the output of weird 1 by just passing integer 1 into the context-dependent selection operator. Take a minute to respond. Let me go through the code to show you what's happening there. I'll scroll down to this one. So this is my data frame, right? PD pandas dot data frame, calling this constructor to create a data frame object. The way that I'm creating this data frame object is using a dictionary-like structure. So the dictionary, the keys to the dictionary are going to be column labels. So one column with the label 1 integer 1, one column with the label 1 as a string 1. And then the values that are stored in each one of those columns are passed as a list. So the first value in the first column is going to be top dog, and then the second value in the first column, which is at location 2 and 1, is going to be bottom dog, and then top cat and bottom cat. So if I go ahead and run it, you'll see that this is how it looks like. Visually, you can tell apart like what's happening between this one and this other one. We mentioned in the previous lecture that we can't have duplicate column labels, but these are not duplicate. One is integer, one is a string. So Pandas has a way of distinguishing between these two features for us. Automatic labeling for the rows, a row at integer position 0 and 1, label 0 and 1 correspondingly. And then here we're using context-dependent extraction, right? I'm passing only one value, right? And that only one value is integer 1, right? So let's go back to this example. If you look at this plot on the right-hand side, you'll see that we say, if it is a slice, it's a row number. This is not a slice, it's a single value. If it is a list, it's a list of column labels. It's not a list. Again, it's a single value. And then if it is a single value, it should be a single column label. So the result is going to be that column. So it's going to be a series object corresponding to that column. So let's see what you all responded. Top dog, bottom dog is the correct response. So let's run it and see. Top dog, bottom dog. You can see that this is actually the name or the label for the series is 1, which is what we were expecting because that's what we extracted. The data type is object because the values are a string. So that's all you need to know. And obviously with the way that it's printed, it's a series object. So let's do one more practice. What happens if I change that 1 to like 1 in a string? Okay, moving on. Let's see what you responded, top cat, bottom cat, because we're extracting just the second column. So if I run it for you to see, we're extracting second column with the label 1. This time it's a string, but we're extracting the second column. Obviously, the second column has cat attribute, top cat, bottom cat, which is what we have. Now this one, what do you respond to this other question? So this time I'm passing a slice. Any volunteer to explain what's going on here? I'll take from this section. Any volunteer from this section? Yes, go ahead. Mm-hmm. Exactly. So the response was that because we're using a slice or we're passing a slice to this context-dependent extractor, it's integer position for the rows. So assume that this is .iloc, and then you're passing you're passing the slice one column, and then you're also extracting all of the columns that we have. So in this case, the slice of one all the way to the end here is basically the last row that we get. So this is the bottom dog and bottom cat is what we get, which is one row. The output type is a data frame because that's how it should be structured. So great work on this exercise. Moving on and just talking about, I briefly mentioned, why do we prefer this context-dependent extraction versus loc and iloc? A lot of times it's the main reason is because it's faster, and just typing a lot of times .loc, .iloc is going to add up, and it would be easier for us to just, if we want to extract, for example, the column candidate, we just directly say, give me the column candidate instead of saying .loc, give me all the rows, comma, then the candidate column to be able to extract it. So it's going to be a little bit easier, but it's going to take you some time to get used to using this context-dependent extraction. But again, you'll use it more frequently than you think right now. So now let's change gears and talk a little bit about conditional selection. So here we were just directly saying what labels we want and what integer positions we want. But what if we have a condition that based on that condition, we want to do extraction? We can do conditional extraction using a Boolean series by passing a Boolean series to the loc operator or to this context-dependent square bracket operator. So the way that it works is that what we can do is we can create a Boolean array or a Boolean series that is going to define the condition that we have. So whatever condition that you have, you're going to apply it to all of the rows independently, and then each one of the rows is going to have an associated Boolean value. What we will do later is we'll pass this Boolean series object or this array to a data frame, and all of the rows that has a corresponding true value are going to be selected in the output. Anything else is going to be filtered out for that purpose. So for the rest of today's lecture, we're going to work with a baby names data frame. This baby names data frame is a data frame of the Social Security registration of babies who were born in different years with different names and the counts of each one of them and the sex that was associated to that baby at birth. So this is an example of how we're extracting the top 10 rows of this data frame, and it's ordered, I believe, by year. So you can see that the top 10 rows are from 1910, and I think the most recent data and this data frame is from 2020 or 2021. We'll see later. So notice how I'm getting the top 10 rows here. I'm saying that .loc. So give me the slice of this data frame that has the row labels starting from the beginning all the way and including 9, because loc was inclusive of the right-hand side. So that's what I'm getting, is starting from 0 all the way to 9. And then I'm saying, give me all of the columns. That's why all of the columns that exist in the data frame, you're seeing them in this output. If I want to perform any conditional selection or conditional filtering on this data frame, what I can do is I can have a Boolean array, a Boolean list, or a Boolean series that the size or the length of this Boolean list is the same as the length of my data frame. So here, the data frame that I created has only 10 rows. I'll pass a list with 10 different values. And these values are Boolean because this is a Boolean list. And it has true and false values. And what happens is that when we're passing this list into this context-dependent extraction, all of the rows that correspond to a true value, those integer position rows are going to be selected to be retrieved in the output. Anything else is going to be filtered out. So here, the first element is true. The first row is going to be preserved, and then so on and so forth. All of the false rows are not going to be selected. And then this way we'll apply this Boolean condition or this Boolean list to the entire data frame that we have. What do we get as a result? We get all of those rows that correspond to a true value. So you can see the correspondence between this row, and you can double check them with the row labels that we have. Question?
Like the index has changed now. Like would that be 0, 1, 3, or does it look weird? I look weird before.
Very good question. The question is, when we're doing the selection, would the index change? So would we have 0, 1, 2, 3, 4 instead of 0, 2, 4, 6, and so on? The index wouldn't change. So think about any row as a dictionary item that the key is the label and the value is the value to the row. So you're moving the entire dictionary item over, including the key is going to be transferred. If you want the labels to be like 0, 1, 2 all the way, you need to reindex it. And we talked about how we can do reindexing in a previous lecture. Good question. So this is how we can just directly decide which rows we want to select and then be able to select those rows based on this Boolean kind of array or list, and then be able to kind of perform the selection. If you are a loc person, we can do exactly the same thing with loc. So instead of just doing a square bracket and pass the context-dependent selection, we can say .loc and then pass the list. In both of the cases, what it does is it will get that list. It will treat that list as an indicator for which one of the rows should be selected, which one of them should be filtered out. So either what I had before is that we can use .loc or we can use a square brackets context-dependent extraction. Either would be fine in this case. But as you can imagine, if we have tens and thousands of rows, we don't want to go ahead and create manually true false values for tens and thousands of rows. And that would be very repetitive and like very inefficient to do. Instead, what we learned in the previous lecture was that we can use Boolean expressions in order to define a condition for whether the rows are going to be preserved or whether the rows are going to be filtered out. So in this case, what you're seeing here is that I created a logical operator series object, and this series object is going to be a Boolean series object that is the result of applying this Boolean expression to each individual row. So what happens is that we're going to select the sex column, we're checking it against the value, a string value f. If the value was equal, then the result for that row is going to be true. Otherwise, the result is going to be false. That's why it is a series that has a corresponding value to each one of the rows, and it's a Boolean because the result of this Boolean expression is either true or false. So let me go ahead and show you how this can be done. Okay, let me restart. Okay, so loading it again, and then all the way to this new data set. So you can see the head of this data set, meaning that the top 5 rows and all of these columns that we get. And what I want to do is I want to go ahead and create this logical operator for you so that you can kind of inspect and see what I mean when I say that we're creating a Boolean series object. So I'll create a logical operator. This is very similar to what we did with the series object last time. I'll say that go ahead and get baby names data frame. Remember that the data frame that I created is called baby names. So go ahead, inspect the baby names data frame. Go ahead and grab the sex column, right? What do we get as a result? We get a series object. So I'm looking at only one column. And notice that this is a context-dependent extraction. I'm passing only single value, and that single value is going to extract only a single column. So I have that. And then I'll say that go ahead and apply this bitwise operation to all of the rows, and then go ahead and tell me whether, not the bitwise operation, this vectorized operation to this entire series object, and check if the value is equal to a string f. And what I'll do is I'll show you what the result look like. Logical operator here. So this is a Boolean series. What can I do with it? I'll do exactly the same thing that we did with the series object previously. It's just that this time, now this series can be used to filter out the entire data frame as opposed to filtering only for one series object. So I can go ahead and say baby names. Sorry, I realize this is a small. Baby names, logical operator, and then be able to see the filtered version of the data frame with all of the sex values be equal to f, as opposed to, I guarantee you that there are male babies there too. But this is kind of a filtered version of our data frame. Notice that I can also do exactly the same thing with loc. So I'll just copy this over, and then with loc, it will basically be that dot loc, passing the logical operator as the locator for the rows, and for the columns, I'll say I want all of the columns, okay? And then what I'll get is exactly the same, or I can just say that go ahead and just give me names, and then I'll give me only the values for that name. But this is only like female baby names that we're getting in the output, okay? Notice that with the loc, the initial case that I showed you was by selecting all of the columns. With the loc operator, passing the second operand is not necessary. So if you don't pass the second operand, it will by default assume that you want all of the columns. But the first operand is necessary. You have to index true rows. And then with the second operand, if you want to make a selection, you provide that. If you want all of the columns, either say colon or don't provide anything, and it will give you all of the columns that you want. So this is all we talked about. We're creating this series object. We know that this series object has Boolean values, and this is what the output of that series object was. We're using this to index into the rows of the baby name. Notice this kind of a inner expression that we're adding to this context-dependent operator. This is going to be used in order to do filtering for us. This is the output data frame. Again, I said that we can do exactly the same thing with loc. So here I'm passing the Boolean series object to index for the rows, and the columns, I'm specifying that with colon, or I could have just removed it and not have that, and I'll end up with getting exactly the same output. As you can imagine, the logical expression that I had was simple. I was just checking for one condition. What if I want to combine multiple conditions so that I have a compound logical expression that I can evaluate? We can basically use a lot of bitwise operators in order to do that. So we can do and, we can do or, we can negate a logical expression, and we can take XOR. So a lot of those variations are available to us. So let's take into account the example of OR. So this is the AND operator. This here is the OR operator. So this vertical bar, if I have two logical expressions and I use OR in between them, this means that if any of them were true, the output, the output is going to be true, and then that row is going to be returned. Specifically in this example, I'm checking for the sex to be F, and then I'm checking for the year to be before the year 2000. So in this case, I'm getting this output where you can see that there are some male baby names that are in the data frame because the year is before the year 2000. So that's why they're included in this output data frame. I talked about this bitwise operators. There's a lot of these bitwise operators. There is the negation. So tilde is the negation. So if you have a logical expression and you want to calculate the negation of that for whatever reason, you can use tilde. Or an and, we talked about it. And then there's X or the caret kind of operator here, which is basically when applied to P and Q operands, it will tell you, it will give you true if only one of those operands is true. So if both of them are true, the output is going to be false. If both of them are false, the output is going to be false. Only if one of them is true, the output is going to be equal to true. So let's do another fun Slido exercise. So there is a question about what does negation mean on a Slido. Negation means that whatever value that you have, you negate it. If it was true, the negation of true is false. If it was false, negation is true. So let me read the question. The question is, write a pandas statement. Which one of the following pandas statements returns a data frame with the first 3 baby names with the count greater than 250? So you can imagine that there is an and going on somewhere, and then there is count that has to be part of this logical expression, and there's also filtering that you have to do on the rows so that you get the top 3 rows. But there are different ways that you can do it. We can do it with logical expression, or we can do it with just directly doing loc and iloc into the data set, because we know how the data set is structured. Okay, let me go to the code to show you how it looks like. Okay, so I said that the output, just the hint in the Slido exercise was that the output should be exactly this. The top 3 rows with the values greater than 250 are associated with, and we only want name and count column. They're associated with row at index or at index 0, at index 233, and then 484. And then what's happening here is that I can use iloc and just go ahead and get those integer positions, right? So in the original data frame, notice that name and count are at what position? Integer position 0, 1, 2, 3, and 4. They're at integer position 3 and 4. That's why this is the column integer position selection that we're doing. For the rows, we already have those row integer positions. The integer positions for the rows is equal to the labels for those rows because they were automatically created. So that's why 0, 20, 233, and 484 are the labels for the rows. So if I do run it, then you'll see that the result is exactly the same. We could do the same thing with the loc, but there is an issue with this second option with the loc. Can someone tell me what the issue is? So the row selection seems to be correct. Yeah. You're in the right direction. The answer is that we're only selecting on the rows. Remember that I said that with loc, you don't necessarily need to pass the second operand for the columns. And if you don't pass the second operand, it will give you all of the columns. That's exactly what it's doing. It's giving you too many columns that you want. But what you're interested in is only this portion of this data frame. So you're not doing proper selection on the columns. The other operations that we have, they are a little bit more logical. So here we're saying that apply this condition so that you only have a number of rows with their count being greater than 250, and then go ahead and select the columns with the label name and count. So far, so good. This is going to be essentially name and count for all of the rows that are that have a count greater than 250. But then we're saying that head tree, give me the top tree. And this compound version is going to give us exactly what we want. If I remove the head tree to show you what this output is, this is going to be this filtered version. But since we want only the top tree, I'll just add this head tree to get the top tree kind of instances. What about this one? .loc, we have the same condition. So we're filtering, and now we're getting this big, all of the number of rows that are that the count is greater than 250. We're getting name and count. So far, it's equal to what we had in the previous option, but we're doing iloc. So we're feeling fancy and we're doing iloc. What's the issue there? Exactly. The answer was the slice is exclusive with the iloc, meaning that it's going to give you row at integer positions 0 and 1, not including tree, right? So this is going to give you only the first 2 instances as opposed to 3 instances. This was a little bit tricky. Okay. So far, so good. Moving on. The correct responses, majority of you selected that. Wonderful. So moving on to a little bit of a more fancy stuff, because we started from just passing this Boolean list. We said that, oh, giving this Boolean list for tens and thousands of rows is going to be very difficult. Then let's go ahead and define these logical expressions that we can use them to index and select for the rows. But what if I have multiple different values? And if I want to, for example, say that I want to check if the name is Bella or Nargis or Alex or Lisa, I have to just enumerate over all of them and then be able to like make this complicated compound logical expression. But what Pandas is going to provide is that Pandas has a lot of different utility functions that in today's lecture, I'm just going to go over some of them so that you see what functionalities are available. Again, we don't want you to remember all of them. We just want you to have heard about them and then see that with Pandas, all of the function names are really kind of meaningful and easy to understand. When I say is in, it looks like that we're searching for something inside another thing or another list, which is exactly what we're going to use for doing the search of the names from a list of names that we have. So let's get into that. The same example that I had, which here was checking whether the baby name is equal to Bella in this case, or the baby name is equal to Alex, Nargis, and Lisa, and we're taking or between each one of these expressions. What I'm going to do next is I'm going to put all of those names in a list. It's very easy to do that. And then it's also easy to create that list from different external sources or from your data frame itself. Say I'm creating that list, and then I'll say that, okay, my Boolean condition is going to be that let's get the names column and let's check if the value that you have in each one of those rows is in the list of names that I have in this list. Just read that as that. Okay, what is the result of this inner expression? The result of this inner expression is true or false. For each one of those rows, we'll go ahead and check whether the value in the column name for that row is in the list that we have. Then the result is going to be true or false. And obviously the rest is simple. That Boolean kind of series is passed to be indexed to be used as the index of the baby names, and the result is going to be filtered accordingly. One other, a little bit of a fancier function that will go over this, I think about 3 lectures from now, is using stir functions. The stir functions are a set of functions that are applied to string values. If you have a column with the string values, all of the string functionalities are available to you through the stir library. So we say .stir, and then there is a bunch of functionalities that are available, again, if your column is of a string type. So for example, in this case, I'm saying that go ahead and get the names column in the baby names. Assume that this is a string and use this function starts with n in order to figure out whether this expression is true or false. If a name starts with n, the value is going to be true. If the name doesn't start with n, the value is going to be false, and then so on and so forth. And then this is going to be able to be used in order to index into the data frame. So you can see that the output data frame only has names that are starting with n. So these are nice functions. Again, I just used 2 examples to show you that the values, we can make use of the values that are stored in the data frame in order to filter a data frame. And there are a lot of utility functions that we have that we can do that. We'll see more of these stir functions again in one big lecture that we'll talk about textual data. We'll see them. We'll see them there, but this is kind of a teaser for you to see. We can make use of these string values as well. So now we have seen how we can filter the data. We have seen how we can do filtering by like constant kind of indexing, by conditional filtering, and then also with utility functions to do conditional filtering. But what if we want to modify a data frame? Because so far we have not been modifying the data frame. We have just been filtering the data frame so that we focus on a small piece of the data frame. What if we want to add a column? What if we want to modify a column? What if we want to drop a column? So all of those things, we're going to talk about them in the next few slides. So adding a column, we can just create a column to a data frame by directly using a square bracket operation here. And this is square bracket operation here. When we're passing the label for the column, it will automatically go ahead and create a column with that specific label that you pass to this square bracket operator. So this is the first time that you're going to use that label. As soon as a new label is going to be used in reference to a data frame, that column is going to be created. How do you assign a value to this newly created column? What is the underlying data type? It has to be a series object. So if you have a series object or some kind of an array with the same length as the data frame, then you can directly assign that series object to be stored in your data frame. So this way you can think about your data frame as a collection or a dictionary of different columns. The labels for those dictionaries are basically column labels, and the values are the values that are stored in each one of them. And it works exactly in the same way that the dictionary works. So in dictionary, as soon as you reference to a new key, that new key is going to be created in the dictionary, right? And then it will wait for you to assign a value to it. It works exactly in the same way. So in this example, I'm also creating another fancy example for you because I use the stir function. I just want to create values that I want to store in the new column. So I'll say that go ahead, get the name column. Know that the values are string values, and go ahead and get the lengths of each one of those name values, right? So here, the result is going to be a bunch of different numerical values that are stored into a series object. And then what I'm going to do next is I'm going to reference to a column label that I want to store the series object, and then I'll go ahead and pass the series object itself for it to be stored in the data frame. So let's go ahead and give it a try. So I'll go ahead and say name lengths is here. It's going to be a series object. So I'll go ahead and say baby names, go ahead and grab the name column. And I'm going to just get the lengths of each one of these entries in the name column. So let's see how it looks like. So you'll see that the length is exactly the same as the length of my data frame, but I have values that these values correspond to the actual name lengths that I have in the data frame. So what I'll do next is I'll just, in exactly the same way that we are adding another key value pair to a dictionary, I'll go ahead and say baby names. I want to create a new column that I'm calling name lengths. And I'll say that the value should be this name lengths object, which is a series object, right? This is the first time that I'm using it. Name length underscore lengths doesn't exist in my data frame. But if I go ahead and let me change this to display and also change this to display. Baby names, you'll be able to see them side by side. This was the series object that I created. Now this is the data frame that I have. And notice that this last column is appended to the end of the data frame that I have. Okay. One more thing that I want to show you is I can modify this data frame that I created or this column that I created. So I can directly go ahead exactly the same way that you can modify a value that's associated to a key in your dictionary. I can go ahead and say baby names for the column name lengths should be equal to, say, exactly the same column, but I just want to reduce the value by 1. For whatever reason, like I have first name, last name, hypothetically, and then I have a space in between, so I just want to remove that space, or any kind of modification that you want to do. As long as the right-hand side is a series, you can just reassign it. So that series can be an existing series object that you have in a data frame. It can be a modified version of that series or an entirely new series that you want to replace. We can do that. Baby names. And you can see that the values are reduced. So previously I had 4, 5, 7. Now I have 3, 4, and 6. Okay. One more thing is sometimes you might want to add a column. You'll do some operation based on that, and you want to remove it. Or for whatever reason, you just want to remove a column, right? We can also remove a column, and then we can say, let's go back to the slide so I can show you. So this was the syntax for adding. This was the syntax for modifying that we just saw. Okay, before moving on to the removing, we can rename a column. If you just want to rename it, you can call .rename and pass a dictionary. The dictionary is gonna have key and value pairs for every previous column labels that you have and any new column labels that you want to give. This is a previous column label. This is a new column label that I want to give. And then you can keep adding dictionary items to this dictionary, and then you can do renaming of a lot of different columns all at once. So in this case, you're seeing that now name lengths has turned into lengths column as the label. This is useful because a lot of time we're getting external data sets and the column names might not exist, or you might create, for example, features and you change your mind and you want to refer to features with a different label so that like it's more readable and it makes more sense. So we will use renaming a lot in Data 100. We can drop a column or drop a row. If you're not interested in a column anymore, we can just say baby names dot drop. We will provide the column that we want to drop, but there is a caveat here that by default, if you call drop, a row is going to be dropped. If you want a column to be dropped, you have to specifically say axis equal to columns, and then a column is going to be dropped. What happens if I don't have that? It's going to go ahead and search through the row labels. It's not going to find a row label with the lengths, and it's going to give me key error. So always be careful about that. Or if you pass a column label that doesn't exist, again, it's going to give you a key error. Think about everything as key value pairs in a dictionary. So let me show you directly that here. So I'll say baby names. Was it baby names? Yes. Baby names dot drop. I'll say, so here I didn't change the name to length, so I'm just going to use name lengths, which is what I had before. Or let's actually drop a state. So let's go ahead and drop a state, and then let's not pass the axis to see that we're going to get an error. So here it says that, scrolling down, the state is not found in axis. So this does not exist in the row labels that we have. So what I'll do is I'll say here that axis equal, was it axis? Yes, axis equal columns. And then in this case, you're seeing that the state does not exist anymore in my data frame. So one interesting fact here is that if I go ahead and print baby names, what's happening is that I'll still see the state. So what happened to me dropping that column? It creates a copy. So every time that you're modifying a data frame, Pandas is going to assume that you don't want to override the original data that you have. So imagine that if you're doing a bunch of exploratory stuff and you keep overriding the original data set and you will lose your data set, by default, it will create a copy. And unless you say that you want to override the previous data frame, it won't override it for you. So in this case, it does drop the data frame, the state from my columns, but it doesn't override it in the baby names. It's stored in some other local copy of a data frame. If I want to keep the changes permanent, I need to specifically say baby names equal to this copy, this new copy. And then when I run it this time, you'll see that now California does not exist anymore. Okay? This is very important. There is another way that I can do it. Say, for example, I would say that, okay, I want to drop one more thing here. I will say that I want to drop, say, column, say, sex from here. I'll say, let's drop sex, and then axis equal to columns. And then let's see if that happens. Oops, sorry. It won't do that because I already dropped this state once. So Control X, I'm going to go to a new cell. So here. So I'll go ahead and just say that drop this new column, and then what I'm getting as a result is that the column is dropped. But again, when I go ahead and say baby names, as we all know and we just learned, the changes are not permanent. Sex column is still in the baby names data frame. The other way that I can do it, there was one way that I could just directly assign override the value of the data frame with this new copy of the data frame. There is another way that I can do it, and that's called in place. I'll say that make the changes in place. So when you drop it, I know what I'm doing. Just go ahead and make it in place. Don't create a new copy. So this is also another way. So this time when I call it, now you can see that the sex column is also gone. So two ways, reassigning or explicitly telling it that you want the changes to be in place and permanent. So I covered a lot of these slides, just quickly seeing what we did. We did drop a column. Here, you now see and you know why I'm reassigning the value. But then we also learned that if I don't reassign it, a new copy is going to be created and the changes are not going to be permanent. So if I just say drop without in place, without reassigning, the baby names is still going to have that column or that changes that we haven't made. So given the timing, I'm going to keep going and not give you a break because I want to cover some utility functions. It's going to be fun, I guarantee you. When you keep learning all of these functionalities, you'll see how much tools you have in order to play with data frames, and then you'll get closer to being able to do homework 2A and homework 2B, which is very exciting. So utility functions, all of the NumPy functionalities are, you can apply them on numerical columns. So for example, in this case, I'm saying that go ahead and filter out the data set. So here I'm feeling fancy. I'm filtering out the data set for all of the rows that has the baby name being equal to Yash. Yash actually is in your content team. And then I'm going to say that now kind of cascading all of these selections, right? One time I'm filtering. Now it gives me all of the Yash rows with all of the columns. Now I'm saying that, okay, only give me the count column. So this is what I'll get as a result. And then what I can do is I can just apply any of these NumPy functions that you learned from data 8. And then also in lab 2A, you'll play with a lot of these NumPy functions. I can say that calculate the average number of babies born with the name Yash over the years, starting from like 1910 all the way to 2020. It looks like that 17, on average 17 babies were born with the name Yash. Give me maximum. What is the maximum number of Yash babies who were born in a given year? That's 29. So a lot of these functionalities are really available on pandas. There's NumPy that's available. There's a lot of these utility functions that are also available that we're going to go over just a selected number of them, and we'll leave it to you to explore the pandas API documentation more to learn more about them. Every time in homeworks and in assignments and projects that we need a new function, we'll give you a link to the API documentation so that you can go and read and learn and then be able to apply it. But most of the time, everything that we need from you is going to be covered in at the high level, at least, it will be covered in either the lecture or in the discussion. So what are the other utility functions? We can get the shape, we can get the size. We previously saw it in the previous lecture. What is shape? When you call shape on a data frame, it will give you how many rows you have and how many columns you have. This is very important. Like the first time that someone gives me a data set, I'll do two things. I'll first get the head of the data set to see like what I have, and then I'll get the shape of the data set to see how many rows I have and how many columns I have generally, to get a sense of what that data set looks like. Those are the general top two to-go things, to-go functions that I'll use when I have a new data set. What is size? Size tells you the general capacity of your data set. It's just the number of rows multiplied by the number of columns. If you're interested in just estimating what the size of the data set would be in terms of like memory and things like that, then you will just call dot size. Describe function, which we used in the lecture 1 demo, is very interesting. You'll use it very frequently. It will give you some summary statistic about the numerical columns that you have. So in the baby names data set, what were the numerical columns? There was year that was numerical and there was count that was numerical. Everything else was categorical. It was a string object type. So what it gives me is some summary statistic. It will tell me the count of the number of elements that are stored in each column, mean, standard deviation, minimum, maximum, and then also it will give me quartiles. Generally, it will give you a sense of the distribution in your data. Why is it useful? It's useful to just get a sense of what's in your data and whether your data has enough kind of information that you need for modeling. For example, for year, I now know with the minimum being 1910 that that's the earliest year that I have, and then the maximum is 2022. So looks like that we updated the data set, so it's better than 2020. With the count, for example, the maximum is interesting. It will tell you that in 1 year, there was one baby name that was very popular. More than 8,000 babies were named with that specific name. Minimum tells you 5. So that tells you that there was one very unique name that on a given year, only 5 babies were named with that year, with that name, and so on and so forth. When we call describe on a series object, it's going to give you a different insight. So for example, I'm going to just apply it on the sex column. What it tells me is it tells me, and notice here that I can apply it on any column with any kind of value, not necessarily numerical value. So in this case, when I'm applying it to the sex column, it will tell me how many unique values we have. Here we have female babies and male babies. So number of unique instances is 2. It will tell me that the most frequent of the 2 is female. And then it will tell me the frequency of female babies in the entire data set across all of the years. Okay, so this is how you can just also get a sense of how the data in one of the columns or for one of the attributes look like. We can do also more fun things. Towards the middle of Data 100, we're going to talk about sampling and then figuring out the distinction between a population and a sample, and then how to use a proper sample for modeling. So we can treat our data frame as a population and then sample instances from that population. We can do that with .sample. .sample is going to give you one instance. If you just call it without any argument, it will give you one instance, and it will do that without replacement. If you want to do sampling with replacement, you'll pass the argument of replace equal to true. So some examples. I just say baby names .sample. It'll give me one random sample. And it depends on how you're setting the seed for your randomness. If you set a seed every time that you sample, you're going to get the same row. But if you don't have a seed, it will every time randomly, it will give you a new sample. You'll learn more about what that seed thing is, I think later in one of the homeworks or one of the labs. We can select more than one sample. I'll say I want 5 samples. Passing an argument to sample is going to give me 5 instances. All of these instances are without replacement. Again, if I want with replacement and I can kind of tolerate having duplicate rows, I can just say replace equal to true and then get with replacement samples. Now, again, I'm feeling a little bit fancier. I'll say .iloc, and I'm passing 2 arguments. I'm saying colon, meaning that give me all the rows. That's the slice for the rows. And then for the columns, I'm saying that give me the integer position starting from 2 all the way to the end. Starting from 2 is where this is integer position 0, 1, 2. So it starts from here all the way to the end. It's going to give me all of the rows that I sample. So you can see that we can really chain all of these functions and all of these functionalities together to do the things that we want. We don't need to have multiple different lines for them. And this is what you'll get used to in homework 2 and homework 3. This is a little bit more chain. What are we doing there? So we are doing conditional filtering first because there is a criteria for our sampling. I'm saying that I want to sample from a population of all of the babies who were born in the year 2000. So this is the conditional filtering. Look how far we've come. So now we do filtering, we do sampling and conditional filtering. This is really good. Baby names for the year column equal to 2000. Now you'll get a selection of all of the entries with the year 2000. What do you do next? I'm sampling. How many instances am I sampling? I'm sampling 4. Now I'm saying that I can get samples with replacement. So replace equal to true. That's the other argument that I'm passing. And then I'll do exactly the same thing that I did before. I'm saying that, okay, give me all of these samples, but only give me these features because I'm not interested in, for example, the state and sex information. I just want to get year, name, and count. And we'll do that. Okay. One more thing, value counts. It is very useful to use on series and also on data frame. So when we say value counts on a series object, so notice that here I'm getting name, I'm getting one column, that's a series object, and I'm saying value counts. What does that mean? It says that go ahead and look for unique values and count those unique values. So for the name, it's going to give me all of these unique instances, and then it will count how many of babies with each one of those names that we have. So there are 223 names of babies, Jean, and then so on and so forth. And these are the more unique names that we have at the bottom. The value counts is going to sort values in descending order. That's why you see the most frequent name at the top and then the least frequent name at the bottom in this case. If we want to only get the list of unique values, instead of also getting unique values along with the counts, we can just directly call unique. I'll say, go ahead and grab the name series, go ahead and get the unique names that are appearing in this entire data set. And it'll give me an array with all of those names. And you can also go ahead and double check that the values are exactly the same in this unique option and also in the list of values that I had in the value count that I got. What I can do is I can also sort values. So why do we want to sort values? Because again, a lot of times We might want to sort by year. We might want to have some structure. If there's earning, we might want to sort by the earnings that we have in our data set. We can call sort values on series or on data frame. And by default, sort values are going to sort values in descending order in the same way that value counts sorts frequencies in descending order. So again, getting names, sorting values. What does that mean? Actually, this is ascending order. By default, it's ascending. So getting name, sort values. So the names are going to be sorted in ascending order. This is ascending, sorting string values is going to be alphabetical ordering sorting. So this starts with all of the names, starting with A all the way to the names that are starting with Z. If I call it on a data frame, it's going to be slightly different because I have to say which column should you use for sorting. So sort based on the name, sort based on the count, sort based on the combination of name first and count second, so on and so forth. So in this case, I'm saying that sort by the count column and ascending is false because the default is ascending. If you want it to be descending, then you can say ascending is equal to false. So now here you're seeing that the data frame is sorted by the count. So we have the most frequent ones at the top, and then it's in descending order. Okay, interesting stuff. It will take time for you to kind of memorize what kind of functionalities exist and then use them hundreds times to kind of remember how to use them and how to chain all of these functionalities together. In the next lecture, I'm going to start from here. I'm going to talk about how we can do custom sort. Custom sorts are very interesting. Then we're going to talk about how we can do grouping and merging, and then more advanced pandas and stuff. So I'll see you back on Thursday.